All right, so we're looking at the carbon cycle today, and right here, this is a really good picture of what the carbon cycle is. Um, think about what you've learned as far as like the water cycle. Um, just kind of the same thing, right? It's the cycle of carbon through the different processes that happen on Earth. Um, on the slides that I have shared with you on Google Classroom, make sure that you watch this video. He does a really good job of talking about the carbon cycle and how it works and where it goes. So make sure you watch this before you continue on. So if you're at this part, pause this, watch this video, and then come back and I'll kind of explain a little bit more what's going on. So the carbon cycle, this is just most of Earth's carbon. It's a lot, and it's mostly stored in rocks. So when you go outside, you find a rock. Okay, that's that type of stuff. That's where most of the carbon on Earth is found. Is in those rocks. Okay, and then the rest is found somewhere in the oceans, in the atmosphere, plants, soil, and then the fossil fuels that we know of. Carbon's always flowing between those in some way. And there's two different cycles. There's a slow and a fast. And then any change in the cycle that shifts carbon out of one reservoir will put carbon in another reservoir. And these changes can result in warmer temperatures on Earth. So the carbon cycle, over the long term, the carbon cycle seems to maintain a balance. This just prevents all of the Earth's carbon from entering the atmosphere all at once. If you think about the planet Venus, okay, that's kind of what's happened. All the carbon dioxide on Venus is in its atmosphere, and so it's made everything really, really, really warm on Venus, and that's not quite the case here on Earth. What's happening on Earth is, there's just this constant cycling of carbon between one place to another, and then back and forth and back and forth, and so it allows for our temperatures to maintain a little bit nicer temperatures. The thermostat works over a few 100,000 years as part of the slow carbon cycle, which means that it is a shorter time period. It's 10 to 100,000 years, and the temperature of Earth can vary. All right, this is a look of those temperature changes, right? So, you can look at this and see where those temperature changes have occurred. All right. Earth swings between ice ages and warm interglacial periods on these timescales. Parts of the carbon cycle may even amplify these short-term temperature changes. All right, so again, you can look and see where the Earth has gone into really warm periods, really low cold periods. All right, and the carbon cycle does play a role in those short temperature changes. So like I said, there are two carbon cycles. There's the slow carbon cycle and the fast carbon cycle. And through a series of chemical reactions and tectonic activity, which we'll look at in a few units, carbon takes between 100 to 200 million years to move between rock, soil, ocean, and atmosphere in the slow carbon cycle. And on average, 10 to the 13th to the 10 to the 14th grams of carbon move through the slow carbon cycle every year. In comparison, human emissions of carbon to the atmosphere are on the order of 10 to the 15th grams, whereas the fast carbon cycle moves 10 to the 16th to 10 to the 17th grams of carbon per year. All right, so these would be exponents. So you would take 10 times 10, 13 times to get that number. So the slow carbon cycle in the atmosphere, the movement of carbon from the atmosphere to the lithosphere or rocks, or the lithosphere also being the crust of the Earth, begins with rain. Atmospheric carbon combines with water to form a weak acid, otherwise known as carbonic acid, that falls to the surface in rain. The acid dissolves rocks, a process called chemical weathering, and releases calcium, magnesium, potassium, and sodium ions. Rivers then carry these ions to the oceans, or in the case of the Great Salt Lakes or the Dead Sea, right, carries those ions to inland waters that get collected in those bodies of water. In the ocean, the calcium ions combine with bicarbonate ions to form calcium carbonate, the active ingredient in antacids, and the chalky white substance that dries on your faucet if you live in an area with hard water. In the modern ocean, most of the calcium carbonate is made by shell-building organisms and plankton. After the organisms die, they sink to the seafloor. Over time, layers of shells and sediment are cemented together and turned to rock, storing the carbon in stone, lime, otherwise known as limestone, and its derivatives. Okay, you also get sandstone, but most of the time it's a limestone in the oceans. The slow carbon cycle on Earth, only 80% of carbon-containing rock is currently made this way. The remaining 20% contain carbon from living things, right, such as limestone. Okay, that would be those living things. Heat and pressure compress the mud and carbon over millions of years, forming sedimentary rocks such as shale. In special cases, when dead plant matter builds up faster than it can decay, layers of organic carbon become oil, coal, or natural gas instead of sedimentary rock like that shale. The slow cycle returns carbon to the atmosphere through volcanoes. Earth's land and ocean surfaces sit on several moving crustal plates. When the plates collide, one sinks beneath the other, and the rock it carries melts under the extreme heat and pressure. The heated rock recombines into silicate minerals, releasing carbon dioxide. When volcanoes erupt, they vent the gas to the atmosphere and cover the land with fresh silicate rock to begin the cycle again. At present, volcanoes emit between 130 and 380 million metric tons of carbon dioxide per year. For comparison, humans emit about 30 billion tons of carbon dioxide per year, 100 to 300 times more than volcanoes by burning fossil fuels. Chemistry regulates this dance between ocean, land, and atmosphere. If carbon dioxide rises in the atmosphere because of an increase in volcanic activity, for example, temperatures rise, leading to more rain, which dissolves more rock, creating more ions that will eventually deposit more carbon on the ocean floor. It takes a few 100,000 years to rebalance the slow carbon cycle through chemical weathering. The slow carbon cycle contains a slightly faster component, which is the ocean. At the surface, where air meets water, carbon dioxide gas dissolves in and ventilates out of the ocean in a steady exchange with the atmosphere. Once in the ocean, carbon dioxide gas reacts with water molecules to release hydrogen, making the ocean more acidic, right? Remember the video that we just watched, right? This is that acid oceans that they're talking about. The hydrogen reacts with carbonate from rock weathering to produce bicarbonate ions. Time it takes carbon to move through the fast carbon cycle is measured in a lifespan. The fast carbon cycle is largely the movement of carbon through life forms on Earth, or the biosphere. So, like we said earlier, about 10 to the 15th to 10 to the 17th grams of carbon move through the fast carbon cycle every year. Carbon plays an essential role in biology because of its ability to form many bonds, up to 4 per atom, in a seemingly endless variety of complex organic molecules. Many organic molecules contain carbon atoms that have formed strong bonds to other carbon atoms, combining into long chains and rings. Such carbon chains and rings are the basis of living things. For instance, DNA is made of 2 intertwined molecules built around a carbon chain. The bonds in the long carbon chains contain a lot of energy. When the chains break apart, the stored energy is released. This energy makes carbon molecules an excellent source of fuel for all living things. Plants and phytoplankton are the main components of the fast carbon cycle. Phytoplankton and plants take carbon dioxide from the atmosphere by absorbing it into their cells. Using energy from the sun, both plants and plankton combine carbon dioxide and water to form sugar and oxygen. The chemical reaction looks like this. Carbon dioxide plus water plus a little bit of energy makes sugar and oxygen, which is released back into the atmosphere. 4 things can happen to move carbon from a plant and return it to the atmosphere, but all involve the same chemical reaction. Plants break down the sugar to get the energy they need to grow. Animals, including us, eat the plants or plankton and break down the plant sugar to get energy. Plants and plankton die and decay and then are eaten by bacteria at the end of the growing season, or fire consumes plants. In each case, oxygen combines with sugar to release water, carbon dioxide, and energy. The basic chemical reaction looks like this. The sugar plus oxygen makes carbon dioxide, water, and energy. Okay, plants breathe out the oxygen, we breathe out the carbon dioxide. In all 4 processes, the carbon dioxide released in the reaction usually ends up in the atmosphere. The fast carbon cycle is so tightly tied to plant life that the growing season can be seen by the way carbon dioxide fluctuates in the atmosphere. In the northern hemisphere, winter, when few land plants are growing and many are decaying, atmospheric carbon dioxide concentrations climb. During the spring, when plants begin growing again, concentrations drop. It is as if the earth is breathing. So this is just showing you the fast carbon cycle. And so here's where that carbon dioxide, this is showing that fluctuation of the carbon dioxide, right? So here it's really high in the northern hemisphere, and then it drops, and then it starts climbing again in September. Okay, here's another thing, right? So land and ocean carbon dioxide, or not carbon dioxide, oxygen. So here you can see all the green and the blue is where all the oxygen is coming from on Earth, right? And then in December, right, it goes away in the northern hemisphere because we're experiencing winter, right? But here, this is the hottest part of the summer, right? And then the winter, okay? Left unperturbed, the fast and slow carbon cycles maintain a relatively steady concentration of carbon in the atmosphere, land, plants, and oceans. But when anything changes the amount of carbon in one reservoir, the effect ripples through the others. In Earth's past, the carbon cycle has changed in response to climate change. Variation in Earth's orbit alter the amount of energy Earth receives from the sun and leads to a cycle of ice ages and warm periods like Earth's current climate. Ice ages developed when northern hemisphere summers cooled and ice built up on land, which in turn slowed the carbon cycle. Meanwhile, a number of factors, including cooler temperatures and increased phytoplankton growth, may have increased the amount of carbon the ocean took out of the atmosphere. The drop in atmospheric carbon caused additional cooling. Similarly, at the end of the last ice age, 10,000 years ago, carbon dioxide in the atmosphere rose dramatically as temperatures warmed. The shifts in Earth's orbit are happening constantly in predictable cycles. In about 30,000 years, Earth's orbit will have changed enough to reduce sunlight in the northern hemisphere to levels that led to the last ice age. Today, changes in the carbon cycle are happening because of people. We perturb the carbon cycle by burning fossil fuels and clearing land. When we clear forests, we remove a dense growth of plants that had stored carbon in wood, stems, and leaves, or biomass. By removing a forest, we eliminate plants that would otherwise take carbon out of the atmosphere as they grow. We tend to replace the dense growth with crops or pasture which store less carbon. We also expose soil that vents carbon from decayed plant matter in the atmosphere. Humans are currently emitting just under 1 billion tons of carbon into the atmosphere per year through land use changes. So without human interference, the carbon in fossil fuels would leak slowly into the atmosphere through volcanic activity over millions of years in the slow carbon cycle. By burning coal, oil, and natural gas, we accelerate the process, releasing vast amounts of carbon into the atmosphere every year. By doing so, we move the carbon from the slow cycle to the fast cycle. In 2009, humans released about 8.4 billion tons of carbon into the atmosphere by burning fossil fuels. So this is just a look at the carbon dioxide emissions per year, every year up to 2008. So again, you can see how our burning of fossil fuels, our burning of carbon dioxide, or our emitting of carbon dioxide in the atmosphere is on the rise every year. Since the beginning of the Industrial Revolution, when people first started burning fossil fuels, carbon dioxide concentrations in the atmosphere have risen About 40%. This means that for every million molecules in the atmosphere, around 387 of them are now carbon dioxide. Okay, it's the highest concentration we've ever had. Methane has also been on the rise, and we're putting a lot of not great stuff in our atmosphere. All of this extra carbon needs to go somewhere. So far, land plants in the ocean have taken up just over 50% of the extra carbon people have put into the atmosphere. Okay, while about 45% of that has stayed in the atmosphere. Eventually, the land and oceans will take up most of the extra carbon dioxide, but as much as 20% may remain in the atmosphere for many thousands of years. The changes in the carbon cycle impact each reservoir. Excess carbon in the atmosphere warms the planet and helps plants on land grow more. Excess carbon in the ocean makes the water more acidic, putting marine life in danger. So here's the effects of the carbon cycle. It is significant that so much carbon dioxide stays in the atmosphere because CO2 is the most important gas for controlling Earth's temperature. Carbon dioxide, methane, and halocarbons are greenhouse gases that absorb a wide range of energy, including infrared energy or heat emitted by the Earth, and then re-emit it. The re-emitted energy travels out in all directions, but some returns to Earth where it heats the surface. Without greenhouse gases, Earth would be a frozen minus 18 degrees Celsius. With too much greenhouse gases, Earth would be like Venus, where the greenhouse atmosphere keeps temperatures around 400 degrees Celsius. So here's the effects on the oceans. About 30% of the carbon dioxide that people have put in the atmosphere has diffused into the ocean through the direct chemical exchange. Dissolving carbon dioxide in the ocean creates carbonic acid, which increases the acidity of the water. Or rather, a slightly alkaline ocean becomes a little less alkaline. The pH of the ocean surface has dropped by 0.1, a 30% change in acidity. So again, go back to that video we just watched. If the oceans get too acidic, there's going to be marine life that just dissolves because of the acidity of our oceans. Plants on land have taken up approximately 25% of the carbon dioxide that humans have put into the atmosphere. The amount of carbon that plants take up varies greatly from year to year, but in general, the world's plants have increased the amount of carbon dioxide they absorb since 1960. Only some of this increase occurred as a direct result of fossil fuel emissions. With more atmospheric carbon dioxide available to convert to plant matter in photosynthesis, plants were able to grow more. This increased growth is referred to as carbon fertilization. Models predict that plants might grow anywhere from 12 to 76% more if atmospheric carbon dioxide is doubled, as long as nothing else like water shortages limits their growth. However, scientists don't know how much carbon dioxide is increasing plant growth in the real world because plants need more carbon dioxide to grow. All right. And we are going to look at a lot of these different things in the next couple of days. So you guys will be able to kind of see this. And so I want you guys to look at this and start thinking about what you believe about climate change. Just kind of based on this information that I gave you about the carbon cycle, start thinking about what you believe about climate change. All right.